Hey guys, welcome. I'm gonna run into an example here that this was a question in the Discord channel, in the Bifrost channel, Discord. Basically the question was how we can have points in an object. Let's take a sphere, for example, and have a vector that wraps around uh, this object, right? And goes around, around, around without going out. Just wraps around any object. Um, so there's different ways to do this. I'll explain you the ways that I know, and then you can decide which one to use. They're all gonna give you basically the same result, but knowing these techniques, um, it won't be specific for this effect. It works for this, but you can use it on different things. So you decide which one you want to use. There are ones that are a little bit more involved, but I felt like it's good to know all this stuff because you can use it in different scenarios, not just this specific scenario. So let's start. Sorry, I'm gonna create a group here because I wanna just uh, have more objects here to use later. So I'm gonna say input geo, create graph, and then I'm gonna bring this here and on the name. I'm just gonna create this expression that I talked about this before, which allows you basically just to grab everything that is inside this group transform, right? Right now it's just one object, but for example, if I add a torus here, and I put it inside and I give it a little kick, look at this icon again. This is one object, and as soon as I update this, it's gonna change into this hat, which is an array because we have more than one object now. I'm gonna hide this, and what I'm gonna do is just say get from array, so I can pick. I'm gonna delete this input and output, and then create a terminal here, so I can pick in which object I want to work with, either the torus or the sphere or whatever else I'm gonna have here, right? I'm gonna create a pass. So if I need to change this for whatever reason, the input, I don't have to disconnect and connect different inputs, different wires here. I can just all from here. I'm gonna press T so we can see a name as well of these nodes, so it's a little bit more clear. Great. So as I was saying, that we need to create a custom vector here that goes around this object. And for that, we can use some data. If you press W between the wires, you can see what kind of data this sphere comes with, and we have something that is useful for us, which is this point normal. To visualize this, we have the point scope. Oops, not that one. Point scope. And by default, it's going to show you the point normal, the color. I don't like this, so I'm going to change this and also make the point smaller. I'm just going to leave it just white. Hide the grid, make this a little bit nicer. And by default, if I enable arrows, here's now be looking for this property, which we don't have. So I'm going to just copy and paste point normals, and there you go. There's another way now in 2.7, which is new, which is called mesh scope as well. And obviously that's what it does, that's what it says. It's gonna give you information about the mesh input, any input mesh that you have. By default, it's gonna give you the points. You can see points like this. You can see point tags. Remember also that in 2.7 now you can input component tags. So for example, real quick, if I create a component tag actually on the sphere, so I can do face real quick, and I say give me a let me call it I don't know, my faces, and let's do another one with points. So I'm gonna do vertex and then create some here, and then that one, say my points, so you can see points and faces. I'm gonna hide this. Now if we press W, we're gonna see those two. So we have face, my faces underscore tag, and then we choose see the points, my points underscore tag. So first it's gonna Bifrost is always gonna give you point underscore and underscore tag. Those are reserved words, and obviously the first is telling you what kind of tag is going to be this one if it's points, vertex, or edges, for example. And that's why you have faces and points, and then you can see the component as well. So for example, if you wanted to see my point tag, I can say point my points underscore tag, and basically, oops, underscore, no. And this is going to highlight those points, as you can see here. So if I, this might be a little bit difficult to see, but if I press 4 now, you can see those points highlighted right there. Or we can just see those points. You can change the color of these guys too if you want to. And you can see connectivity as well, which is also very useful. You can see the edge connectivity between the mesh or the face, the point face neighbors as well. This is super useful to have this data when you manipulate this later on if you are trying to visualize something. Change color again. You can see vertex IDs, displays face IDs, which is useful. Again, you have the face underscore my faces, I think it's called, tag. And these are a little more easy to see because our faces, and it also highlights those, and you can change obviously the color for this to whatever you want, or just show the faces that are tagged and all that stuff. Face IDs, and then also we have vertex normals, point normals, and face normals as well as vertex normals. So all this is great. Take a look, have a fun, play with it. It's super useful to have this around. Again, it's new to 2.7. Anyway, let's get back to our task here. So we have this data, the point normals. What we want to do basically is grab these vectors and cross them so we can get the third vector. We can get this orthogonal vector. And the way that we can do that obviously is with a cross product. And we have a node that in Bifrost, which is going to grab vector A, B, and it's going to give you that orthogonal vector. So what I'm going to do is going to get the point normals, connect this right here, and then just to see this, I'm going to set the point normal for now, because we want to see this. So if I connect the point normals, it's that. If I connect the cross, nothing is going on because we don't have yet another vector. So I'm going to use the up vector here. I'm going to create a value from here so we can see it clearly, and then I'm just going to output an up vector. And that basically give us this vector here that goes around the object. It's giving this orthogonal vector, this third vector. So you can change this, obviously. You can do it negative, so it goes the other way around. You can do it in X, right? So we get the other vector in Z or in C, right? And we get that in X. So again, you can do whatever you want here. We're going to start simple and we're going to customize later on. So we have this vector, and what we want to do is use this new vector that we have this into our particles. So I'm going to create a basic particle graph here, right click, explode, oops, and I'm going to delete the collider because we don't need it, and connect just this directly, the point normal, into the geometry. I want to change this to 1001 because my timeline starts at that, and now we have points. They're too big again for my taste, so I'm going to make it smaller and hide the point scope. Since we want to use this in velocity, I'm going to set the point velocity, because at the end of the day, that's what we want to do here. So point velocity, and actually I want to connect this here. So now our normals, if I preview from here, they're going to be back to, we are not manipulating that data, just back to what they were. So now it's point velocity. So if I check, again, I can prove this. If I check now point velocity, we have that vector going around. But the normal is back to what it was. Great. All right, so I'm gonna delete this point normal here. Alright, so if I press play, they go down because by default Bifrost has the gravity on. So I'm going to turn that off, go back to the beginning, press play. Now what is happening that these points basically are flying along the normals, or it looks like it, and it is actually. Again, we're looking at the velocity here, but if we look at the normals, basically all these points are going towards just shooting along normals. If, for example, to prove this very quickly, what I can do is just do a sequence array here, so you believe me. Well, actually, never mind, and I don't have to do this. I'll prove it in a different way, but that's what's happening because by default we have this normal speed, and basically that is just shooting all these points along normals. And then we have a speed, so if you up this speed, they're gonna go faster. So if I go back, now they're shooting faster. If I turn this off, now the points are gonna get born, but they don't have any forces or anything, nothing affecting them. As you can see, they're popping in and out because by default also the age limit is 2 seconds. So I can say live forever, and now they're gonna live forever. They're gonna born and they live forever. Cool. So now to take into account this, we need to tell the source particle to inherit that velocity coming from the geo, from these points. And now we see that is inheriting the velocity, as you can see. And as you can see, what's happening here now, all the points that are being born are inheriting that velocity, but then after a few frames, after the aging, these points basically, they get born, they start going toward that velocity, but then when they're aging, they start spreading apart from this mesh. And that was happening, right? Because on each time step is updating and it's giving that direction, and then this velocity is not updating on each time step. It's just on emission. It's reading this once, read it, and it keep going, the solver. So if we will go back to the beginning here, oops, and let's go to the top, and it's playing frame by frame. You can see that these points going around, and they start aging, right? And the momentum start going out of the way. So that's what's happening. The reading and the new points are just, again, read, and then it's going up. So that's what happens. So what we need to do basically is keep this velocity, or actually read this velocity on each time step and push these points back to this mesh, which is a sphere right now. So we want to push these guys in. And there's a few ways to do this, I explained in the beginning. I'm gonna go with the longest one, and then I'll explain the rest of them. So let's start. All right, so let's start. All right, so the first one that we're gonna do is it's gonna be inside the solver itself. You might know or might not know this, but if you right click, you can make this editable, and then basically you can customize this as you wish and change stuff on the solver, so it's open solver. It's not a black box anymore, any of the solvers in Bifrost. So what I'm gonna do is connect this guy into the solver, and then also, so we don't have any velocity here, I'm gonna connect this guy here and disconnect out and move this out of the way. So now if I press play, the points are being born, and that's it. So I'm gonna rename this in geo, so we keep it, and basically I need to do a few connections here. So particle, and I know this is not the most friendly way to do this, but you do it once and then you forget about it, and hopefully this is gonna change in the future, so we'll have to do this. And then we have this guy custom effect here, which I want to connect the in-geo into here. And finally we arrive where we need to work on inside the solver. And even though as you can see here, we have a sticky note here where say custom effects might be added by the user, and you can set properties on the particles to pass the result into the set particle, which is this guy. So basically all your work needs to be done in this wire or in this chain, and leave this solver object intact and then just work here. So that's where we're gonna do our work in this change. I'm gonna delete the get particle solver settings because I don't need it for this. You can always add it back if you want to. I know it's kind of deep inside, and again, hopefully this changes in the future, but this is just one way to do this. And then I'm gonna show you a way that is a lot simpler than this. But again, as I said at the beginning, I'm just showing you different options here, and you can decide which one to use. And also, as I said at the beginning, this is just one way to work, and then you can use these techniques for different things. All right, so I'll get the geo here, and I'm gonna create a pass so it's easier to connect to. And what we need to do basically, and what we will do, is use the same velocity that we created outside. Now we're gonna use it inside. I'm gonna copy paste that, and if, for example, you go ahead and you try to connect this straight into the particle solver here, and then you get the normals from the geometry, right? And you press play, you're gonna get this weird thing going on here. And why this is happening? Well, you're getting the normal from the geo, which doesn't match the point count that is being passed here. And if you try to connect this here now and you press play, nothing's gonna happen because obviously there is no normals inside here. So there's a few things, you know, that are not completely working. And there is no right now. I mean, obviously you can create a particle, and you can actually source or set a particle here. A property, and call this point normal. But this is gonna just be read on emission, so it's basically the same. So it doesn't really work in this case. So what we need to do basically is grab our geo here and get the closest location. So we're gonna use actually this our little friend here to sample the point normal. So we are getting the closest location from this geometry, and which position? Well, we don't want to grab the position from the geometry. We want to get the position from the particles. So I'm gonna say get point position from here and grab the position from here, so we can sample that. So now we get the closest location here. Let me make a little more space. And what we need to do when we have this data is sample this. So I'm gonna sample a property, and you already guessed which property we need from the geo, the locations. It doesn't know which property we want, even though by default it's point position. You need to tell the default that it's going to be a vector. It can be any property, by the way. It doesn't have to be point position, and right now we don't need the point position, we need the point normal. So we're getting the sample point normal, and if I now connect this straight here and press play, look at what we got. We got basically something similar to what we were getting outside the solver, but now the points are going around. But you notice a behavior that is a little bit weird here, which is basically these points are getting we have the points going around the sphere, but again we are not pushing back. It's not pushing back these points back into our sphere that is right here, right? So that is the next step that we need to do. So I can delete this now, and for that we can use, and also just by the way, so for example, if you want to spice up this a little bit, or like let's say I put 0.5 here and let go back, and then I press play, it's gonna do that. It's gonna do the same, but let's say that you want to add a little noise here, you know, your own noise. Some say fractal turbulence field. We're gonna sample this field. We're gonna grab the positions from the particles again, right? Sample it, and we want to modulate this. So I'm gonna say time just to fill, because we have at the time it's in on field, so we need to modulate this and convert this into a field. So now if I connect this and then we add this noise into our velocity here, right? As soon as I do this, this is gonna go completely out of the shape. I mean, it's cool in its own way, right? But it's not really what we want. And then you can also apply, I mean, you don't have to do this, by the way, here. You can do this simpler, actually, in the influence, and then just set the property, the velocity or force outside here, or even apply a turbulence field. So this is nothing really that you cannot do outside the solver, but I'm just showing you what's happening as soon as you add your own little field here, or noise, right? I'll change this a little bit because I want to play with this. So let's say 5. I'm gonna lower the frequency to 0.4 and I don't know, 0.35 or something like that. Let's see what we get. And actually also want to speed up this. So I'm gonna multiply this. We're gonna create a value node here and connect that, and let's multiply by, I don't know, let's say 4 now. Let's see how that looks. Okay, cool, yeah. So you see how it speed ups and they're gonna slow down with the frequency and all that. Cool. So now we have a modulated noise here, and then when we adding that into the velocity, as you can see, it's not keeping the points in the on the mesh. So for that, what we need to do is use our old trusty closest location again, and what we need to do is just copy paste this, but instead of getting the normals now, we're gonna sample the point position. If I sample this and we set now the point position on the particles, and we connect this right here, now we're gonna get the effect basically that we were looking for. Very cool. I'll change also the points here. I'm gonna go back to the beginning, and what I'm gonna do, actually, I'm gonna scatter some points, and because I want to control how many points I want to, and 1,000 is fine. I want to emit only once, so I'm gonna use end frame, just on the first frame, and then finally I want to say pass through points. So we use the points from the scatter, and this is exactly 1,000. And if I press play, we're gonna get the same effect. But now it's a little bit simpler to read and what's happening and all that stuff. Very cool. So there you go. That's one way. And what I'm gonna do, I'm gonna go to the range slider here and then just shorten this a little bit so it's not as long. Okay, I'm using the full screen window here. That's why you see this. All right, so this is one way to do it, and hopefully that makes sense. What I'm doing here, again, getting the closest location from the sphere, then sampling the normal and the point positions, and then basically we're doing the same thing that we did outside with the point normal, crossing with a vector, with a different different vector here, and adding that and adding this noise, modulating noise, into the velocity, and then basically sampling the point position and then setting that point position back to the particle. So we push all these points back to the mesh. Alright, so the other way that we can do this is with a volume, with sampling a volume. So if I press play, so we can get the same behavior now, we can just use sample volume, and sample volume gradient, these two. And for this to work, what we need to give it is an SDF, a volume, and a specific an SDF. I can actually create an SDF from the geo right here, but mesh to volume, for example. However, this won't be very efficient, obviously, because we're computing or making this SDF inside the solver, so it's going to be calculated. So what you want to do is create this actually outside the solver, since you just want to compute this once and forget about it. And then hook it up in here. Now this is not going to work because everything is connected to the closest locations, and the closest location doesn't work with volume data. So now that we know that this is a volume, we can connect that here and in the gradient to get the gradient as well. If we press W right here, we're gonna have some properties, which are voxel properties, and what we need, oops, before I change, we need to make sure that it's an SDF, not a fog. By default, this is a fog, so we need to convert this into an SDF and make sure that, I mean, you can leave it relative. The only difference is that it's gonna be a little bit more, it's not gonna be as accurate of a mesh. So it's up to you what you wanna do here. And by the way, real quick, another way to convert this into an SDF is mesh to level set, and then you have the convert to volume, which is a higher level node. And they all do the same, except this one, which actually you cannot convert, you cannot get a fog from here. With this one, you can actually output both or just the SDF. With this one, you just output a level set, and with this, you can do both as well, plus you have more options, and then you have a fan import, which means that you can connect as many inputs meshes as you wish and convert all those at the same time into an SDF or a fog. So it's actually pretty useful to have this. This is going to be the fastest way, and you can find these two actually in the convert to volume inside the high level node. So with that said, I'm just going to keep the mesh to volume. I'm going to make sure that it's an SDF, come back to custom effect now, and now we can make sure that this is going to be a voxel sign distance, which is the property that we need. So I'm going to put it right here, voxel sign distance, copy this and paste on the same to get the gradient. And the other thing that we need actually is the positions, and we're going to get the positions from the points, from the particles. So there you go. So now we have all the data that we need, and now we can use these guys too. So now we have the SDF and then the gradient. So the SDF, I'm gonna explain this a little bit quicker here. So an SDF basically is going to give us the distance to the surface, and more like to the iso contour basically of the surface. So if I draw, again, we have the sphere here, but let's say that with the sphere, it's going to give us basically this distance right here, right? This, and this distance to the surface, the iso contour, right? And so an SDF values that are inside the mesh is going to be negative values, and outside are going to be positive. And that is what the sign means in this, by the way. Distance is the distance to the surface, the closest distance to the surface, and field is because we are dealing with fields, distance field usually is what it's called. Excuse me. So that's what we're getting here, right? Hopefully that was a little bit clear of what I'm talking about here. Let me delete this now and go back to 1. Okay, sorry about that. So, and then we have the gradient, which basically is a direction vector, and basically that also could be negative or positive depending how you want to get it. And this basically allows you to determine a vector pointing in the direction back to the closest surface. And that's basically what the volume gradient does with an SDF. So when I use it that way. Alright, so in order to do that, to get actually a direction back to the closest surface, we need to multiply this. There's the gradient. You can also, by the way, think of a gradient as the normals of the vector. If you want, I mean, you can think like that. It's not really that, but you can think it if it doesn't make it easier. Anyhow, so we can multiply this with an SDF, which really should normalize this vector here, just for a safety measure here. And basically then what we need to do is, let's say that we have let me go back to red here real quick. Let's say that we have a point here and then another point here, and let's call this vector A and this vector B, and then you want to get a vector back, right? What we need to do, because we need to subtract this, so it's important the way that if I put a subtract node here, it's going to be important how you hook up this. So if you want to get a vector back to the surface, basically we need to subtract A minus B. And if you want to get a vector the other way around, then you do b minus a. So that is just something to keep in mind. So that is why it's important how you connect these nodes. So in this case, we want to get the positions from the particles and subtract with our new vector here. And basically this is going to give you the direction to the closest surface, and this is going to go to the positions. And now if I hook up this, it's going to go back to normal. Let me delete this again. And if I press play, nothing is going to happen because the velocity now, still we're sampling the point normal with the locations which works on a surface or point. So what we need to do basically is the same thing here. So I can just connect this. And if I press play now, this is going to work, as you can see. And now the points are still there. But if you want to get the whole velocity, what we can do is just copy this, right? And then just do it right here with this new vector, with the gradient basically. So did I copy that? No, I did not. So let me say Control C, Control B, and basically grab the gradient here, cross that with the same vector, and we can add this right here with the noise again, and then add this into the velocity. So now we have the same velocity that we were using before. And I believe, okay, so the position change and the velocity. I disconnect this on the wrong way. Okay, so now again, we have our noise, our field noise here that is modulating, right? And we're sampling that with position of the particles, and we are adding the cross product of the gradient basically, and then we are still getting the positions back. So now if I press play now, we have the same motion that we were having before. So there you go. The main difference obviously between these two techniques is that this one is dependent of the mesh resolution. So if you compare this to the original geometry, this might be a little bit above, or kind of like it's being pushed out of the sphere, because it depending on, again, of this detail size. The lower you go, the higher it's going to be, and more accurate your mesh is going to be, but the slower it's going to be, obviously. So that is one of the drawbacks. This works in points, so that is actually going to be pretty quickly, and it's not going to have that issue. However, these two techniques that I'm showing you here, like sampling the volume and then working also with a get closest location, none of them really are. What I mean is, like, this is a technique that I use a lot, by the way, getting the distance, because getting the distance of the surface, the closest surface, or getting a vector is used a lot. When you're inside something and you have that data, you can use it to do what we're doing right now, and to do a lot of different effects. So just learning this and learning different ways to approach a problem is actually a good technique to know, a good thing to know. So again, it's just different ways that give you the same result, but so that's why I want to show you these two ways. So these are two ways that we are now manipulating all this data inside the solver. Next stuff is going to be everything that we did, but without using without going inside the solver. So I can actually just create a new simulate particle here, and without using the mesh or the SDF. So let's move on. All right, so now we're gonna do, as I said, everything outside the solver, right? So we're gonna connect the source here and the settings right here. I'm gonna leave this guy here, just back here, and disconnect these guys, but I'm gonna leave it out there so you guys can check it out later on. All right, so we're gonna do everything outside, but now we're gonna play with fields. And the way that I'm gonna do this, I'm gonna reuse our SDF here, and then I'm gonna convert this into a field. For that, we have the voxel field node. By default, this is gonna give us the property that we need, which is assign distance again, and this is gonna be a scalar. It's gonna put a scalar value. A little trick here that you can do is put properties. Just type these parameters. For example, I can say field type underscore type, and that's going to tell me that it's a scalar. Now if I change this to a vector, obviously the data type that we have inside is wrong, but it's going to update that. So it's kind of neat to see this in the node itself. I can also just add another one, for example, so I can say property, and now this is going to tell me basically that is the property that is a scalar field, is a form, it's a design distance, and this is useful because sometimes you want to know exactly what you are calling and if it's a scalar or a vector. Obviously, you can also create a value node here, and that is going to create a scalar here. Anyhow, just a little tip there for you to use on your nodes if you want to see the information right in the node and not go into the parameters. Cool. So we have the sign distance, and basically what we're going to do here is going to be basically the same as this, but now with fields. So what I'm going to do, actually I'm going to steal the noise from here because we're going to use the same noise. No, why not? Control C. I'm going to paste this right here now. We have the noise, cool. And what we need to do now is cross this, right? So we can create our custom now field. We're gonna cross the sign distance. Actually, we need to get the gradient, I'm sorry. So, how we did here, we got the sample in the gradient. In field, we have a gradient field. So we just need to give it the SDF, and then we have a gradient field. To visualize fields, we have two scopes, vector field scope, and then we have the scalar field scope. Oops, sorry, scalar field scope. So if I want to visualize what the gradient is, I can connect that here, and then let's bring the terminal back into the game here. I'm connecting to a proxy, and as you can see, if I go back now, you can see what that field looks like. And as I said, before on this, that you can think it as like a normal for the volume, even though it's not, but if it does make it easier, you can think it like that. So we're gonna leave this on, and we're gonna cross now the gradient by an add vector. So I'm gonna say vector field because now we're dealing with fields, so everything needs to be this kind of brown or orange, dark orange, or whatever you want. I don't know what color it is. It's kind of like a little sand color in a way. And if I connect this here, now we won't have anything because there is no vector here. So I'm gonna say 0.5. Just keep it the same way that we had it inside, which was 0.5 and 1. Cool. The same thing. Now we have this field going around the mesh. So there you go. Now we can add this into with the noise. This is our field noise here, and if we add this and we see what it's doing, now we can preview what our modulating noise with time, right? And with the cross vector field. And as you can see now, we can see a preview of what is this doing here. And actually, let me, 1 second here. Let me actually turn off this. Cool. I'm gonna press P. This is not doing anything yet. Actually, let me go to the beginning, and you can see that the points are not moving because there is no velocities, no field, nothing is affecting those points, by the way. Now you can see it clearly. If I press play, nothing is happening here, right? So now we have our custom velocity, and what we can do is just set influence property here. Influence set property. Let me get this influence set property and connect this right here. And what property we want to influence? Well, we want to influence the point velocity. And if I connect now this into the influences and I go back to the beginning and I press play, now basically what we have is the modulating noise going around this. And basically this is the same thing that we were doing before, but now what we need to do is use the SDF basically to push these points to the surface. And for that, I'm going to show you two ways. Again, just to show you more and more knowledge is better, right? I'm gonna show you first the manual way to do this, and let me actually create a compound here so we can start cleaning up a little bit of this. So I'm gonna grab this, and this, and say Control G. And now this is gonna be our custom fill bell. And if I go to the beginning, press play, yeah, same, everything's working correctly. And as I said, I'm gonna show you two ways. So I'm gonna show you how to build this manually, and then I'm gonna show you the one node solution. So for that we need an SDF, and basically again it's the same as this. It's just doing what we did right here. So it's nothing that you haven't done before. So again, I can grab the gradient, I can use the gradient there, but already put it in the compound. So I'm gonna just create a new one, normalize this, multiply. I'll do it very quickly because we already saw. Basically, I'm repeating the same thing. Our vector first with the SDF, and then we're gonna subtract the point positions from the particles with this vector. So how we do that? Well, we have this awesome node that is called property proxy fields, and this basically what allows you to do is get properties that are in the simulation, and you can grab any property at any time step basically and influence something else, for example, or use it as you wish after the fact or inside or mid-sim. So basically what I want to grab is the point position. So I can say point position, and we have this little field type here, which is telling us by default this is going to read as scalar field, but point position is a vector, so I need to change this into a vector. Now it's going to change, and now we're reading this correctly. So basically we want to do the same as we did here again, just to repeat myself. We want to grab the point position from the particles, but now with the field. So we're grabbing that point position and getting this vector here, right? And adding another set influence property, but instead of influencing point velocity, guess what we're going to influence? Very clear, it's going to be point position. If I connect now back this here and I press play, now we got the same thing that we were doing inside the custom effect, inside this guy here, inside the simulate particle DAGO. But now everything is outside. It's a little more friendly instead of going inside, and it's all with fields. And fields in Bifrost are very, very fast. So this is the manual way to do this, which is good to know. I'm gonna actually Control G this to create just SDF back to surface, back SDF closest. I'm just gonna say SDF close to back to surface. But instead of doing this, there's a node that we have. But again, I'm just showing you this because this is good to know. Again, if you know how to do it manually, then you can add more to this system, or you can use it in a completely different way, but you know how to do it. But the easier way to do this, we have a node, a field for this, which is called closest point field. And the only thing that you need to fit in is an SDF. And as soon as you do that, that's going to give you the closest point to the surface, and you just connect this into the point positions, and you don't need any of the property proxies and all that. You just set that to the point position, and now if I press play again, it's going to work the same way as you can see here. So this is our one node solution to get the points back into the surface, which is pretty cool because you don't have to do any of this. But again, different ways. Learning how to build this manually is super useful. I'm guessing they're doing something similar. You can open this, a black box node, but my guess is something very similar to this, if not the same. And yeah, and there you go. And basically that is the effect. So now, just to make it a little bit pretty, I'll Let's create a quick color here, but basically we're done with the effect. Now you can stop and go back and do something else. So I'm gonna get the point count here because I need to match the points. Just want to give it a little bit more something, and let's do random color, random color array, and this node is from our friend Jason, which I use a lot of the time. So I'm gonna just create a minimum of, I don't know, blue. Yeah, I have the colors picked up already. Great. And then I'm gonna output this. And what I want to show you next, real quick here, I'm gonna assign diagnostics material. Apply this, change this emission color to a string, so we can just type the property that we need, which is gonna be color. And if I press P now, we have the colors. And if I press play, we get the same thing. Great. And then just to make it even cooler, I'm gonna say create trails, create particle, I think it's particle trail, yes. And connect this guy here, transfer the color to the trails. So comma, color, again, copy, paste this because it's the same, and connect that back into the proxy as well. So now if I press play, we're gonna get some awesome trails plus the points. Cool. And now to show you the final part is that now we can switch this array with something else, like for example the torus, reset the feedback. The shortcut for that is Control R. If you go to the edit, it's gonna tell you here, because it's a solver, you need to reset the feedback sometimes. And if I press play now, this works the same way, as you can see. Very cool. And I have another surprise here. Control R again. I grabbed the dolphin from the counter browser. So if you press this, I grab this guy and import it back. And then if I go back into a get my array, go back to 0, reset the feedback port, we have our little cool dolphin here. And let's add more points. Why not? Let's add 3,000 points or more, whatever. Again, reset the feedback and press play. And now we are getting the same behavior that we did with the sphere or the torus, and all that works great. So there you go, guys. Hopefully this was helpful. Again, I wanted to ask also, just I don't know if you like these videos, the length that are these videos. I try to put as much information as I can in these videos so you guys can learn. Sometimes I know they're like pretty long. I can do like a quick tips, like 10 minutes, 5 minutes quick tips, just to show you different techniques here and there. But I feel like this is, again, I show you different ways to basically do the same effect. It's good to know all these techniques, because again, now we're using for this specific effect, how we can apply the same techniques for one specific, but all these techniques are useful for all kind of effects, all kind of that data. You can use it as you wish. So again, let me know in the comments if these long videos are helpful or not, and let me know also what we'd like to see next. I'll share this file on the Discord channel, on the Bifrost Addict channel, and if you have any questions, let me know there or in the comments below. And until next time, cheers.